Welcome to EDC lecture number 6. Today we will study voltage divider bias configuration and the approximate method to solve for different currents and voltages for this configuration. We have already studied that there is an exact method to analyze this voltage divider bias configuration that requires the help of Thevenin's theorem. In addition to that method, there is an approximate method where we do not need to apply Thevenin's theorem. We can make an approximation or assumption. So let's see what this assumption is. If we have already seen that the resistance that we can see at base terminal is beta times the resistance at emitter Re. Beta Re is the resistance that can be seen by being present at base terminal. Because this is emitter resistance is on the output side and you see from the input side it is being multiplied with a beta. If R2, the assumption is that if R2 is less than or equal to beta times Re over 10, we can assume that the current IB that enters into the base is negligibly small compared to I2. In fact, the current I1 that flows through R1 is split at this junction, at this point, and becomes I2 and IB. If this assumption holds that R2 is less than or equal to beta Re over 10, IB would be negligibly small compared to I2 and we can neglect it. If we neglect the current that enters into the base terminal, this means we have this voltage divider network and the voltage here would be VB, this voltage VB. This VB can be computed using voltage divider theorem. VB is equal to R2 over R1 plus R2 times VCC. Once this base voltage is found, then we can write input loop equation starting from VB minus the base emitter voltage minus this voltage drop and the output loop equation to find IB, IC and VCE. Let's write the input loop equation. The Kirchhoff's voltage law equation for input loop is starting from VB, the voltage at base terminal, VB minus the voltage drop across base emitter junction, VBE minus the voltage drop across Re is equal to 0. This Re can be written as beta times IC. We derived an expression for this in our last lecture. Beta IB. So we can solve it for IB, VB minus VBE over beta times Re. And IC can be written as beta times IB. To solve for VCE, the voltage drop between collector and emitter terminals, we need to write output loop equation. As we have been writing for last so many lectures, at least for last 3 lectures. VCC minus the voltage drop across RC minus this voltage drop across collector emitter minus IERE. Since IE and IC are very close to each other, we can write it as IC, and then VCE can be written as VCC minus IC times RC plus RT. That's all for this lecture, and in the next lecture we will study about the stability that is added into BJT based amplifier if we add an RE. The effect of RE adds stability. We'll see in next lecture. Thank you.